Hey guys, so we are going to look at the question under physics mechanics, which is the conservation of, which is the energy of the system. So now they were given this problem here that an inclined plane of an angle theta is equal to 20 degrees as a spring of a force constant, which is K is 500 Newton meters, fastened securely at the bottom so that the spring is parallel to the surface as shown. And they are saying that a block of mass m is equal to 2.5 kilograms is placed on the plane at a distance d, which is 0.3 meters from the spring. They are saying now from this position the block is projected downwards towards the spring with a speed v, which is equal to 0.75 meters per second, by which distance is the spring compressed when the block momentarily comes to rest. So they want by what distance will the spring be compressed when the block momentarily come to rest. So let's write the data down first. They are saying now there's the incline of theta, which is 20 degrees. So I can say theta here is equal to 20 degrees, and they're saying spring constant now K is equal to 500 newtons meters. We have K, which is 500 newtons per meter, and then they're saying is fastened securely, and they give us that the mass is equal to 2.5 kilograms. Also now they're giving us the distance d, which is equal to um, 0.3 meters, and then now they're giving us also the velocity, initial velocity, or the velocity on which the box was projected, which is 0.75 meters per second. So we want by how much will that spring be compressed there. So now we can use the energy equation. We know that EMAC, the mechanical energy before, will be equal to EMAC, the mechanical energy after. That means after the collision. So now we have work 1 plus EK1, or EK initial plus EP initial, is equal to work finally plus EK finally plus EP finally. So that's work plus kinetic energy plus potential energy. So in the initial position, when the block is there above the incline, we do not have work done because the box hasn't moved any distance, and we do have kinetic energy because they've given us a velocity, initial velocity of 0.75 meters per second. So you can say now 1 over 2 mv squared initially, that is the initial kinetic energy, plus potential energy, which is going to be mgh, mass multiplied by force of gravity multiplied by the height of the incline, is equal to the work. Finally the work will be done by the spring, because the spring does have a certain potential energy since we're given the spring constant. So that's gonna be, according to Hooke's law, work done by spring will be 1 over 2 multiplied by the spring constant multiplied by change in displacement squared. And then also kinetic energy will be 0. We don't have kinetic energy, reason being that now they're telling us when the block momentarily comes to rest, that means we will suddenly stop there. So that means we will not have kinetic energy. The speed will be 0. And then plus potential energy, we also don't have potential energy because we do not have height with a reference to the initial condition there. So let's try to draw now a free body diagram. So can draw something like this, and then see now we have that represented in terms of a dot, and then we have a normal force there, we can say Fn, and then we obviously we have force of gravity, which is Fg, and then we have a perpendicular force there, which is perpendicular to the incline, and then that perpendicular force will be Fg. I'll just call it Fg perpendicular, and then we have the Fg parallel there, Fg parallel. So now we have 90 degrees between Fg parallel and Fg perpendicular, and we're given theta here, which was equal to 20 degrees. That means we have here theta again. So now we can try to see the forces that we have there. We have about 3 forces, which is the normal force, we are not told. We'll assume that the friction force is 0, and then we have the F3 parallel, which is the component. This F3, the F3 parallel is a component of the weight, which will be now the one that is going to also be responsible in sliding the box downwards. And then now we can find that F3 parallel from that triangle of ours. Can see that from theta F3 parallel is opposite divided by hypotenuse, which is equal to F3, and that is equal to sine of theta. That means now F3 parallel is equal to M3 sine of theta. So that is what we have for F3 parallel, and is directed downwards. So now we need also to find our height, the height of the, we need to find the height of the incline. So we know that the spring will actually come to rest a certain distance. So to find the height, we'll be having something like this. So we know that we have a certain height h here, and then we have theta, which will not change, and then of course we have a certain distance here, and then that distance is the one that we are given, that is 0.3. Also we will have a certain distance, additional distance, can call that distance x, and then that will be a distance by which the spring will be compressed before the system comes to rest. So now we can see that to find our h, now we will having now h, which is opposite divided by hypotenuse, which is d plus x. That's gonna be equal to the sine of theta, and then our h should be d plus x, and then multiply by sine of theta. After that, now from our energy equations, again we can substitute the value of h. That means we can have 1 over 2 mv initial squared plus now the m3h, which is gonna be m3 multiplied by height, and then set our height now is d plus x, and then multiply by the sine of theta. That's what we have, and then that's gonna be equal to what? 1 over 2 k change in x squared. So that's gonna be 1 over 2 multiplied by k multiplied by x final squared minus x initial squared. So that's what we have. So again we are having 1 over 2 and then mv initial squared plus, now removing the parentheses there, we're gonna get now m3 d multiplied by sine of theta, and then plus m3 x multiplied by sine of theta. So we're gonna have now equal to, we know that initially the spring was not compressed, so now we can say now we're gonna have 1 over 2 k, we are left with one displacement here with 1 over 2 kx squared. So that is what we have. So now again we're going to have now 1 over 2 mv squared now, which is gonna be, we can substitute the values. Remember, given that the mass is 2.5, and then we were given the initial velocity, that means we can say 1 over 2 into 2.5 squared, and then 1 over 2 into 2.5 into 0.75 squared, which was our initial velocity, and then plus mass, which is 2.5 multiplied by 9.8 multiplied by the d, and the d was 0.3, and then also multiply by sine of 20 degrees, and then plus m, which is 2.5 multiplied by 9.8 multiplied by x, which we want, and then multiply by sine of 20 degrees, and then that's going to be equal to 1 over 2 multiplied by the spring constant, and the spring constant was 500 newtons per meter. That's going to be 500, and then multiply by x squared, of which that's the variable that we want. So now we have 1 over 2 multiplied by, if we simplify there, we're going to have 1 over 2 multiplied by 2.5 multiplied by 0.75, and then squared, and then you say plus 2.5 times 9.81, 9.8 multiplied by 0.3 sine of 20 degrees. and then that is giving me 3.22, in fact 3.226, and then plus, now we are having 2.5 multiplied by 9.81 multiply, let's use 9.8 multiplied by sine of 20, and then I get a value of 8.379, and then I know that now this is equal to 1 over 2 multiplied by 500, which is 250, multiplied by x squared. Of course, we also have the variable x here. That's x is equal to what? 250 multiplied by x squared. So we can say now we have our 250, taking all these other variables to the same side, we're going to have 250 x squared minus 8.379x minus 3.226, and that's equal to 0. So from here we can use a quadratic equation to solve that. We know that now our x will be equal to negative b plus or minus square root b squared minus 4ac, and then we divide by the 2a, and then now we can say now x is equal to negative b, and then our b you can say is coefficient of x, so it's negative 8.379, so 8.379 plus or minus the square root of 8.379 squared minus 4 into a, and then our a is actually 250, and then multiply by our c, and then our c is negative 3.226, negative 3.226. So all divided by 2 multiplied by a, and then we said our a again is what? Is 250, 250. So now what we're gonna have is we're gonna have x is equal to, now we're gonna have 8.379 plus the square root of 8.379 squared plus 4 times minus 4 times 250 multiplied by negative 3.226, and then you say 2 times 250, and then I get 0.3131, is actually 0.1316 meters, or x is equal to, when I'm using the negative sign there, I'm getting negative 0.098, and of course the distance cannot be negative, therefore our x should be 0.1316 meters, and then x is equal to, if we multiply that by 1000, that's 0.1316 multiplied by 1000, that's going to be 131.6 millimeters. So that is the distance that we get. So that's how we can do that question. So the next question here says now, a 600 kilogram fridge car rolls along rails with a negligible friction. The car is brought to rest by a combination of two cold springs as illustrated in the figure. They're saying now both springs are described by Hooke's law, and they have a spring constant K1, which is 1,600 newtons, K2 is equal to 3,400 newtons per meter, and they're saying that after the first spring compression, after the first spring compresses a distance of 30, the second spring acts with the first to increase the force as additional compression occurs, as shown in the graph. So this is the graph that they've given us, and they are saying the car comes to rest 50 centimeter after the first contact with the two springs. So they're saying now find the car's initial velocity. So now again we can use energy equation, frictionless surfaces. We know that now Emac before is equal to Emac after, and then now let's take the data. We have now mass. We do have the mass of the fridge car. We have a mass which is equal to 6,000 kilograms, and then we have also the spring constant K1 which is equal to 1,600 newtons per meter. We have K2 which is equal to 3,400 newtons per meter, and they're saying after the compression, now the first one is 30, so we have x1 which is 30 there according to that graph, and then we have what, the full distance which is 50. So now going back to our energy equation, initially the troll was moving there, so that means we have 1 over 2 mv squared, which is the kinetic energy. Of course, there's no change in height, so the potential energy before and the potential energy after will cancel, and we'll assume we want the velocity of the car just before it compresses the first spring. So assuming that v1 will be exactly before the first compression, so that's gonna be equal to, finally we have work done by spring 1 plus work done by spring 2, and then after that, that's all that we have. So because it comes to rest, that means we do not have a kinetic energy. And then we can calculate now. We do have m, we want the velocity, initial velocity. We can calculate the work done by the first spring, and that work should be 1 over 2 kx squared, which is 1 over 2, and the spring constant we're given, that is 1,600 multiplied by x, and then the x is actually the first spring. If we notice, is that it was compressed from that distance to the end there. That means it compressed 0.3 before the second spring, and then it was compressed again a distance of 20 centimeters after the second spring when they are working together. So when the compression happens here, this troll will try to compress that, and the spring will try to exert a force on the opposite direction due to their potential energy. So now that's why we do have a work that is done by the spring. So the first spring, now it was compressed till the end because it was longer than the second spring. That means we'll take a full distance now of 0.5 centimeters. That's gonna be 0.5 meters and then squared. So that means the first work now will be 1 over 2 and then into 1,600, and then it's 1,600 into 0.5 squared, and then I get 200 joules. And then we have also again the work done by the second spring, which is 1 over 2 kx squared, and that's 1 over 2. Our k for the second spring is 3,400 multiplied by x, and then it was only compressed for a distance. If we look at the graph very well, from a distance of 30 to 50, and 50 minus 30 is 20. 20 divided by 1000 is 0.2. 30 divided by 20 divided by 100 is 0.2, and then that's going to be a squared, and then we have work 2, which is now 1 over 2 into 3,400 into 0.2 squared, and then that's going to give me 68 kilojoules. So those are works that are done by the spring 1 and the spring 2. So going back to our energy equation now, making V the subject of the formula, we're gonna get a square root of, we have work done by spring 1 plus work done by spring 2, and then divided by, of course, multiply by 2 there. So that's gonna be 2 into work done by spring 1 plus work done by spring 2, and then divided by m, and then they are all under the square root. So that's going to be a root of 2 into the first work is 200 joules plus 68, and then divided by the mass which we're given, that is 6,000, and then the velocity initial now I found to be 2 into 200 plus 68, and then divided by is 6,000, and then I get 0.299 meters per second. So 0.299 meters per second, that's it. So yeah, that's how we can solve this problem.